you, Professor Dharma. And first of all, let me thank the Academy for giving this opportunity to speak in this prestigious meeting. So the title of my talk is Sharp Inequalities and Related Problems. Okay. So all of us are familiar with inequalities. Okay. So we have seen various inequalities even from our school days. Okay. So in case some of you have forgotten, I will just recall some of the very elementary inequalities. For example, one of the simplest inequality which you will see this 2xy is less than or equal to x square plus y square. Okay, it's just a restatement of the fact that x minus y all square is greater than or equal to 0. Okay, and then so I have a term like sharp inequality. So what I mean here is this inequality is sharp, for in the sense that 2 I cannot replace by anything better than that. Because if I put x is equal to y, I have equality here. Okay, so I cannot have that. Okay, and sometimes I talk about the extremals of this inequality. Extremals of the inequality, what I mean is when I put a sharp constant, the function for which the equality holds. Okay, so another inequality which you may be familiar is what is known as the Young's inequality. What is known as the xy less than or equal to x to the power p by p plus y to the power q by q, where 1 by p plus 1 by q is equal to 1 and xy element of R. Okay. So this is the same as this inequality when p and q are both are equal to 2. Okay. So there is another inequality which I can say use that something like this, what is known as the Koshish Inequality. Sigma mod xi yi is less than or equal to xi to the power p or to the power 1 by p into this. Okay. I am just giving you some inequalities just to recall what inequalities are. I am interested in inequalities which involves functions. Okay. More importantly, the function inequalities which connects the function and its derivative. That is the focus of my inequality. Okay. So to start with that, so let me start with a function. I am taking an interval AB. Okay, and I am taking a function u. Forget about whatever be this notation. It means that it's a differentiable function and the function vanishes at both endpoints. Okay, so you know that for differentiable function there is something called fundamental theorem of calculus, which basically tells you that you can get back the function by integrating its derivative. Okay, so I just use that u of x square. I wanted to do that ux I write it as integral from a to x u prime t, then modulus square. Then I can use certain inequalities and you can estimate and you can get that is less than or equal to b minus a into integral from a to b u prime square. Okay, and then this again I can integrate from integral from a to b on the left hand side, and that leads to an inequality of this form. Okay, so you can note that the inequality finally what I am obtaining is it connects the square of u mod u square integral with u prime square. I am estimating the norm of u with that of a norm of u prime. Okay, so I have proved this inequality using some very elementary arguments, and I have a constant here. So that does not mean that I can have a better constant there. Maybe my approach was something very primitive. In fact, you can find the best constant. In fact, finally what I can conclude is that there exists an optimal constant lambda 1, okay, greater than 0, such that this kind of an inequality holds. Okay, once a and b are fixed, I can get a constant lambda 1. In fact, it is going to depend on a and b, such that integral from a to b mod u square is less than or equal to integral from a to b u prime square. This holds for all functions, differentiable functions which vanishes at a and b. Okay. In fact, if you know a little bit of ordinary differential equation, one can show that this lambda 1, it has some significance. It's going to be the first eigenvalue of the operator, the second derivative, minus second derivative. Okay. So I'm not going to those details. Okay. Okay. So whatever I have done here is a very special case of a very well-known inequality, what is known as the Poincare inequality. Okay. It is in general dimensions. You have the n-dimensional Euclidean space, and you take any open set which is bounded open set, then what it says that there exists an constant lambda 1 of omega, which I call it lambda 1, greater than 0, such that this inequality holds for all functions which are differentiable ones, and with this I mean that it vanishes near the boundary especially. Okay, So you can, because I need this kind of a condition, because if I put a constant function, this is not true. Because if we have a constant function, this is 0 and this is non-zero. So you cannot allow constant functions. So it is true for in this class of functions. So this inequality is known as the Poincare inequality, and this constant that has an importance, and that's again going to be the, in fact, it's going to be the first eigenvalue of the Laplace operator with the Dirichlet boundary conditions and so on. Okay. So this is another inequality which I wanted to introduce. Okay. So next, now I am interested in, so these inequalities are all in some domains in Rn, bounded domains in Rn. So what happens to this inequality in the entire space Rn? Can I have an inequality like this? That is the first question that I am asking. So can we have this inequality in Rn? Or in other words, can you find a constant C such that integral over Rn mod u square is less than or equal to integral over Rn modulus of gradient of u all square? Or in other words, you take the L2 norm of the derivative or the gradient. Can you control of the L2 norm of the function using that? And it should hold for all functions which are of compact support and once differentiable and so on. Okay. So unfortunately, the answer is no. Okay. And so then I modify this question further. I am going to ask, instead of putting here 2, and I am going to put arbitrary powers p and q. Okay. That's the next question what I am going to, more generally, can we have an inequalities like this? What I am doing is this 2 I am replaced by an arbitrary p, okay? P is going to be greater than 1, and on the left hand side I am, instead of 2, I am putting a q, and all to the power I am putting at p by q. So you may wonder why this kind of strange inequality, because if you want an inequality, it has to be true for all u, okay? So if it has to be true for u, it has to be true for any constant times u. That means both sides of the inequality should be of the same homogeneity. That means if you replace u with some constant times u, the power of constant comes out on both sides has to be the same. That is why I am dividing this with the q, and this is the, if at all something is possible, this is the kind of inequality which you can hope. Okay. So this is the general question which I am going to ask. And the answer is, if suppose you have such an inequality, it is not possible for any arbitrary p and q. And there has to be a relation between this q and p, and this q has to be a function of p which is given by np by n minus p. Okay. From this term itself you can see that n minus p, if this is equal to 0, it has to be a problem and so on. Or if p is greater than n, this is going to be negative and so on. So there are issues. Okay. So if such an inequality holds, there has to be a relation between q and p. Okay. So in fact, in this indeed a theorem, which is what is known as the Sobel of Inequality, which tells you that this inequality is indeed true. Okay. So what I am saying is that you fix 1 less than or equal to p strictly less than n, where n is the dimension, that Euclidean n space dimension, and I take a number p less than or equal to 1, then there exists an optimal constant here such that this inequality holds. This p star is that q what I have written before. Okay, you have an inequality like this. So which tells you that because you take a function, you take its gradient and you take its pth power, and what does it control? It is the u. What power of u it is going to be controlled? Okay, it is this u to the power p star. That p star is nothing but this quantity np by n minus p. Okay. So this is what is known as the Sobel of Inequality, and then there will be natural questions. What happens when p is greater than or equal to n? Okay, it's this gradient of u to the power p on the right hand side. What is it going to control? Okay, in fact there is an inequality when p is strictly greater than n. What it controls is the oscillation of the function. Okay, what we call is the Helder norm and so on. It is this modulus of ux. In fact, there is a modulus here. Modulus of ux minus uy divided by mod x minus y to the power 1 minus n by p is less than or equal to this kind of a thing. So this is what is known as the well-known Morris inequality. So this still remains one case open when p is equal to n. Okay, and that is also known. In that case, what exactly you can conclude is, instead of mod u to the power p star, what you can control is some exponential of u to the power some power. Okay, so that inequalities are also well studied, and what is known as the Moser-Rudinger inequalities and so on. Okay, So this is basically, so what I am going to concentrate is this inequality. This I stated just for the, to complete the picture. Okay, so I am just going to do this. Okay, so you have this inequality. What I am talking about is, so this is the best constant in this inequality, and what I mean by an extremal of this inequality is the function for which equality holds here. Okay, so I want to analyze this case. For that, first I will consider the case P is equal to 1. Okay, so P is equal to 1, then I can rewrite this inequality like this. This is the inequality. I just rewrite when n is equal to 1, this is the inequality. Okay, so that means integral of modulus of gradient of u, what it controls is mod u to the power n by n minus 1, this integral. Okay, so then one may ask, what is this best constant? Okay, and in fact you can calculate that. This is going to be this, it can be written like this, where this omega n minus 1 is nothing but the surface area of the n minus 1 dimensional ball in Rn, or you take the unit ball in Rn and its boundaries of n minus 1 dimensional, its surface area, that is what I denoted by omega n minus 1, and it is known this. Okay, so you have the best constant that is also known in this inequality. And now next question is, if you have such an inequality, can you have equality in this inequality? Can you have some function for which equality holds? Unfortunately, the answer is no. In fact, S1n is not achieved. Okay, so this is purely an analysis problem where you have inequalities. Next, what I am going to tell you is that this inequality is actually equivalent to a very geometric problem, what is known as the isoperimetric problem. Okay, so I am sure all of you know what is isoperimetric problem. That means given a perimeter and which is the shape which encloses the maximum area, or even in 3 dimension you have the corresponding picture. Okay, isoperimetric problem, determine the shape of the closed plane curve having a given length and enclosing the maximum area, or even in 3 dimension you have the same kind of questions. And there is a mathematically rigorous version of this thing, and what is known as the isoperimetric inequality, that is what I am going to state here. Okay, so this is a mathematically rigorous form of the isoperimetric inequality which we have stated here. It is available in any n dimension. It says that if omega is a bounded open set in Rn with smooth boundary, then Hn minus 1 of boundary of omega. This, what I mean is that you take the boundary of omega, it's an n minus 1 dimensional object, it's n minus 1 dimensional area. So on the right hand side you have the measure. Okay, and then this volume can be compared with controlled with the boundary measure. Okay, and then there is a constant here, and this constant is actually the best constant, and you can actually show that if omega is a ball, this you can have in fact equality in this case. Okay, when omega is a ball, boundary, the measure of the boundary and the volume are related, this is going to be equal. Okay, and in fact for a set, if this equality holds if and only if it is going to be a ball. Okay, so you note that this constant here, it is the same as what I have written here, the constant in this inequality. Okay, and it is not a surprise. In fact, there is a theorem due to Federer and Fleming in the 1960s who proved that the Sobel of inequality with P is equal to 1, which I have stated before, is equivalent to the isoperimetric inequality. Okay, so the first one looks like a very analysis inequality. Second statement is a geometric problem, but both are equivalent. Okay, so if you are comfortable with the functions, one can do that, or if you are more comfortable with geometry, maybe you will end up with this. So these problems are all connected. So I just wanted to show that it may look like some inequality, but it reflects various other problems and various other phenomena. Okay, so there was a conjecture in this connection. There was a conjecture on a general Riemannian manifold, not general Riemannian, but what is known as a Cartan-Hadamard manifold. And the conjecture was that the same isoperimetric inequality, what is in the Euclidean space, holds. Okay, and this was known in the 1926 by Weil, and then it was in n is equal to 392. It was proved by Kleiner, Kroc in 1984, and it was open till recently, and in the end of August or beginning of September, preprint has come. We still don't know the validity of that, and which claims to settle the conjecture. Okay, and again this problem could have been analyzed by looking at an inequality. Yeah, inequality. Okay, So that is one, and next we go to the other case like a p is equal to 2, where this is going to be the inequality, okay, and this is going to be the inequality, and then it is known that the extremal functions exist for this kind of an inequality, and then if you have an extremal inequality, then there is a corresponding Euler-Lagrange equation, and the Euler-Lagrange equation looks like this, okay. So if you want to find a solution of this equation, okay, then it is if you can find all solutions of this kind of equation, then that will give you all the extremals of this equation. And in fact, this equation has a lot of structures. In fact, it has a rotational symmetry, and it is what is known as, it has a conformal invariance, okay. Conformal invariance, I'm not going to the details of that. And using all these kind of hidden structures, one can prove that all extremals of this inequality can be compared like this. In fact, given an x0 and an epsilon positive, you can provide an extremal. So extremals are as a family of n plus 1 dimensional functions, you can get it, okay. And this, in fact, this problem is also connected to a problem in differential geometry, and is a theorem due to a beta. Let G be a metric on the unit sphere on Sn, conformal to the standard metric on Sn. Then G is of constant scalar curvature 1 if and only if G is of constant sectional curvature 1. Again, you can show that these two things are equivalent. So again, I am trying to tell you that other things may look like just an inequality, but there are so many hidden things behind all these things, okay. And the reason for, there has been a lot of study based on all these things. The main motivation was from a problem in differential geometry, what is known as the Yamabe problem. And to study this kind of problem, and the Yamabe problem, the Yamabe problem is to given a compact Riemannian manifold, can you find a metric which is conformal to G and so that it has the constant scalar curvature, okay. And it can be converted to a PDE like this. And the study of this, the showing existence of solution to this PDE is a non-trivial problem, and that is closely related to that Sobel of inequality which I have stated, because I don't have time to go into the details why it happens, and that inequality and its extremals and so on, okay. So now let me briefly tell you some inequality which I encountered with, okay. There was an inequality called something like Hardy-Sobolev-Mazia inequality. So here the special feature is that Rn I write in Rk cross Rh, X I write in Y and Z. You have some inequality here, there is a weight which is Y, it is only a partial, not the full X, okay. So when you look at this equation, you can see that it does not have the kind of a symmetry or something which was coming in the previous equations. And what happens is that I was interested in studying this kind of a problem because of a PDE which was suggested by some astrophysicist as some model for some modeling of some elliptic galaxies and so on. And they had a PDE and there was a non-existence phenomenon associated with that, and I happened to study that, and in the process I ended up with this kind of an inequality. I understood that the key issue is to understand how understand the extremals of this inequality, okay. This extremal is a very complicated looking inequality, and then if you have an extremal, you can see that this is going to be the kind of a partial differential equation it's going to satisfy. So then I wanted to show that I wanted to see the uniqueness of solutions for that equation, and the difficulty was the lack of rotational symmetry for this problem or the conformal invariance and so on. So what we did was that in a joint work with one of my collaborators, we were able to find that this problem has some kind of hidden symmetry, what is known as the hyperbolic symmetry. The problem can be lifted to the hyperbolic space of a dimension n minus k plus 1, and there we could and that hidden symmetry we could exploit, and we could using that we could prove that we could prove a classification result for that inequalities, and we could get a lot of information about the extremals and so on, okay. And in some special cases this was more relevant to the problem which was suggested by those astrophysicists, and this was the equation, and we could even classify all the solutions in a very explicit way like this, okay. And so what played over, the important thing was that earlier I was showing the lot of connection with geometry etc. In this equation what we discovered was that there was a connection with the hyperbolic geometry. Okay, thank you so much. I will stop.